Yeah. It was lectures was bit larger.
Yeah. Okay.
Okay, I think are we ready to start? So let's just remember what we were starting out discussing yesterday. We were thinking about partial differentiations, linear operators. So the textbook example is, of course, the Laplace operator. Here we're thinking 2 dimensions. So there it is written out. Yeah.
Close to the laptop.
Okay. Right. Okay. Here.
Close to the laptop.
Which laptop? This laptop?
Yeah.
Yeah. Okay. All right. I like walking up and down. So. get my exercise. I get my exercise when I do. I don't think I can do this.
You can walk like that.
I can just walk a little bit, backwards and forwards. Okay. I will try and stand here. I'm sure I'll forget in about 2 minutes' time to start facing up and down. Okay. So on the Laplace operator, 2 dimensions areas, and we were thinking about how we might study that numerically. And just to make things concrete, we were thinking of a problem we might try and address, which is this notion here, kind of here, the shape of a drum, which means if we have these 2 shapes here, the question is whether the spectrum of eigenvalues of the Laplace operator on these 2 domains, where the displacement is going to vanish on these boundaries, matches up. Turns out, like I said, there's a title which I haven't put in these slides. The answer is actually no. Of course, these 2 shapes here have the same spectrum. So mathematically, that problem, like we said, it was in a. What we have to do is find eigenvalues of this operator. And yesterday we, first of all, wrote down a grid representation of the operator, which is nice and simple. It's just basically a nearest neighbor sum that represents the Laplace operator. So of course, when we have a big grid, which if we're trying to put a fine resolution grid onto our domains, then we have lots of points, but of course the linear operator then is sparse. So to write out this matrix, we had 1,000,000 points, and we have a 1,000,000 by 1,000,000 matrix. If we were to write it out explicitly, there'd be lots and lots of zeros in there. There's only 5 non-zero entries per row or column. So the Landshafts algorithm we looked at yesterday, let's quickly recap, is a technique for finding eigenvectors and eigenvalues for these sparse, symmetric, positive, definite linear operators. Works on curve space. So we looked at the Stern sequence, and I set you as a little sort of exercise. See if you can use this Stern sequence to analyze tridiagonal matrices, such as this nice simple example here, this 4x4 test case. Can you find eigenvalues by studying the Stern sequence that comes from these tridiagonal matrices? So maybe we'll look at that this afternoon as well in the lab session. And so what the Landshafts algorithm does for us is it takes an arbitrary symmetric positive definite matrix, sorry, just symmetric matrix, and generates a similarity transformation that translates that arbitrary matrix into a tridiagonal form, plus a sort of unitary transformation that maps between those 2 different systems. So it generates these alphas and betas, or sequence of them, which are then going to be the diagonal and off-diagonal elements of our tridiagonal matrix. And it generates these V's, set of sequence of vectors, which it turns out will be the columns of our unitary matrix that will map between our original problem and this tridiagonal form. And so now you can see how our Stern sequence, as an example, is going to be useful now, because once we've translated from the original problem to the tridiagonal form, we have some techniques now to start thinking about how to extract information from the tridiagonal form very efficiently, very cheaply, And so that's a much easier system to deal with. And this Lanczos algorithm is going to provide the bridge between the original problem and the tridiagonal form. And then these other algorithms, such as the Stern sequence, will be how we'll extract the data from the tridiagonal form. So we're going to break the problem into these two steps. First step is this Lanczos step, and the second is going to be an algorithm such as the Stern sequence. And so the algorithm on the previous slide is constructed so that we have this orthogonality relationship, which is quite easy to show for the Lanczos sequence. And because of that, so we saw all this yesterday, if we were to construct a whole n of these vectors, we have these square matrices, via our square matrices, if we fill out all of the columns until the sequence stops, and it terminates in exact arithmetic. And provided we don't have any problems where we're only spanning some subspace, we can terminate early. Let's assume that didn't happen. Then we take these vectors and we write them down as vertical stripes in this square matrix V. And then you see the action of applying our original operator, whatever it may be, on any one of these vectors, generates a linear combination of that vector plus the two next door neighbors, if you like, in that sequence, just because the recursion relation we can see above. And so that can be rewritten as just linear combinations, where now this tridiagonal matrix appears on the right-hand side because it's just taking linear combinations of columns. So since we're adding columns up, we need to put this tridiagonal matrix on the right-hand side, and you can see that basically the action, the right-hand side then is just taking linear combinations of nearest neighboring columns, if you like. So we've got this tridiagonal form over on the right-hand side there, which represents, has a sort of physical information of our system encoded in it, and it's representing the action of n in this way. And then because these are orthogonal, then we have a similarity transformation. And so the Stern sequence is a neat way of getting eigenvalues. If we want eigenvectors, then we have to work a little bit harder. We haven't really addressed that problem at all. We've just figured out a way of getting the eigenvalues quite neatly. But obviously enough, we might want to compute the eigenvectors as well. Then there's a set of pretty robust algorithms that will do that job for us. And you can look, for example, in numerical recipes, and take, for example, this set of algorithms which are slightly more work to understand than the Stern sequence, but essentially the tridiagonal form is such a simple, such a useful form to represent this matrix in. These algorithms work very neatly and very efficiently, and there's lots of different ways of approaching the problem, and they're numerically quite robust as well. So with the tridiagonal form, once we've got that tridiagonal form, we're in good shape. And we can write down a slightly more complicated algorithm and get not just eigenvalues, but also eigenvectors. You get eigenvectors at t, but then of course these v's will allow you to relate them back to eigenvectors of m at the original problem. So you'll run some routine like t through I to get the eigenvectors at t, and then you're just taking linear combinations of these v's, and that maps back into eigenvectors of n. So you just have to remember the translation steps to go back to your original problem. But that's quite straightforward once you've got these eigenvectors of t. So I'd be happy so far with that. Good. So now the bad news. The algorithm is pretty unstable, really, when we introduce the real-world problem, if you like, of running these algorithms on computers that use finite precision floating point representations for real numbers. And it's a pretty tough job to get Lanczos to work in practice for large systems. It's quite a difficult routine. Fortunately, lots of clever mathematicians have worked on the problem, and there's lots of quite good canned routines that you can use as well. So there's quite stable numerical libraries that work pretty effectively that allow you to generate eigenvalues and eigenvectors for pretty large systems. But what goes on inside the hood is a lot more complicated than what we've described here. The basic mathematical ideas are what we've described so far, but there's a lot of extra work that has to be done to make these things stable. So the mathematical framework in exact arithmetic is quite straightforward. But the real tough time comes when we have to deal with floating point. It's quite tricky, it's quite fussy. So just a few observations. Okay, so just generally, if you try applying Landschafts for a system that's of any interesting size, thousands of elements in it, for example, then roundoff error quickly piles up, and you start losing orthogonality amongst your vectors, and all sorts of horrible things happen. You start getting spurious modes, extra copies of eigenvectors start to sneak in. It's pretty nasty. One interesting observation is that basically the extreme ends of this spectrum are the ones that converge fastest. So if you're interested in an eigenvector right in the middle of the spectrum, the middle eigenvector, you'll have a very, very hard time. If you're interested in the largest or smallest eigenvectors, then will be generally in more luck. And that's sort of, physically, that's sort of nice because generally speaking, you usually are interested in the two ends of the spectrum. You're either interested in the long distance physics of a problem, which is normally encoded in the low modes of the spectrum of these differential operators, as a general rule. Or maybe you're interested in the very high frequency again. That's the opposite end of the spectrum. So quite often, luck would have it that for interesting physics problems, it's those extreme ends of the spectrum which are the interesting ones. If you're interested in the middle of the spectrum, well, one trick is, of course, is just to perform some mapping on your system that exposes the middle of the spectrum. Takes some linear combination. So there are some tricks you can play that might expose that bit of the spectrum, map it from the middle of the spectrum to the end of a different spectrum. But generally speaking, the end of the spectrum converges fastest. Okay, so how can we fix this problem of losing this orthogonality relation in finite precision? Well, you can re-orthogonalize, so you can use something like a modified Gram-Schmidt. So if you remember what that is, that's just basically having a set of vectors. When we generate a new one, just orthogonalizing explicitly by subtracting off dot products times linear combinations of earlier entries. And that tends to work quite well in general. But of course, it comes with two problems. First of all, it's expensive. There's a lot of extra work. Now you've got to evaluate all of these dot products against all of these other vectors earlier in the sequence. Which, I mean, if you have a set of k vectors and I want to carry out, explicitly orthogonalize them against each other, then I have a set of k squared times n operations that I need to do. That's quite expensive. It's actually also not perfectly numerically stable in and of itself as well. As roundoff error can mess up the modified Gram-Schmidt algorithm too, so it's not necessarily a perfect solution. And of course, the other big problem is we need extra storage. We've got to keep all of these entries in the sequence. If you remember yesterday, we looked at this sequence and recognized that modulo all of these problems, we could overwrite our computer's memory as we went along. We only needed to refer back to a few entries, earlier entries in the sequence, 2 or 3 steps back in the sequence to construct the next step. So we could be overwriting the computer's memory, but this re-orthogonalization step means we have to store those vectors. Yeah.
In practice, are people using householder to orthogonalize?
You can use a different sort of re-orthogonalization trick given these transformations has householding. That's right, but they're even more expensive, right? Because you have to go back and do even more work. You have to go back and modify the entire sequence. With Gram-Schmidt, you're just orthogonalizing the next entry against the previous one. With a householder, when you next generate an entry, you've got to go back to the entire sequence of these shuffles. So it's even more expensive, but it's at least more stable at least. So that is the benefit. Yes, so yes, that's true. But in practice, I don't think that happens much. So these restart tricks are kind of the sort of state of the art, if you like. I think there's one. If you look inside most of those canned routines, they're using these different tricks, these rather than these explicit orthogonalization techniques. So householder works, but it's expensive. So these are a little bit more. There's a more efficient trick. So the alternative is basically just to sort of restart occasionally. So that's the notion of a restart. An explicit restart is what I guess what it says. If you're interested in, let's say you're interested in the low end of the spectrum, say the first 10 eigenvectors, let's imagine. So you would start the Landschafts sequence off with some arbitrary seed vector, and you would propagate for some number of iterations, using, say, Gram-Schmidt to orthogonalize and keep everything sane. And then at some point you'd stop. Now, before you reach the end of the sequence, you stop. As you start to lose orthogonality, as things start to go a bit crazy, as you run out of memory or computer time, whatever it is, you'd stop. And then you would take those vectors and you would run some algorithm that would try to construct the best possible guess for your 10 lowest eigenvectors. Now, there will be an imperfect guess, of course, because you haven't got the entire space. But you make a best guess of what you have. And then you have, some not terribly good approximation to the first 10 eigenvectors, plus some other stuff. So you throw away the other stuff and you keep those two first guesses. And then you seed a fresh sequence by constructing some linear combination of those guesses. So you start off with a new seed, which has got a larger component in that vector space that you're interested in. And you start again. And if we imagine that we did a perfect job and we had some seed that was really a combination of only those 10 lowest eigenvectors, let's imagine we lucked out and got a perfect set of representation of those low eigenvectors, then the Lanchos sequence would actually stop after 10 steps because it would span this little 10-dimensional vector space, this small vector space would be spanned, and it would run out of directions to go. The operator can't get from that eigenspace to the other remaining big eigenspace. So the sequence will actually stop at that point. So you can think about, if I wanted those 10 modes, you can think about what would be a good stopping condition is if the Lanchos sequence just appeared to want to stop after 10 steps. So what we'll try and do is we'll project into that space, try and start with a seed which is sort of as big a component in the vector space we're interested in, run, and keep doing this restarting trick, keep refining our little basis for this small vector space, and keep restarting, and keep doing that until basically after L steps, after 10 steps, the Lanchos sequence appears to want to stop. So that's the notion of restarting. So we keep reconcentrating and regenerating seed vectors that look more and more like they live inside the vector space that we're really trying to probe. So that's the notion of a restart. So it really is generating a Lanchos sequence, refining it in some way to extract the information we're interested in, concentrating the information we're interested in some small subset, and using that to restart another sequence and iterating that until we get this convergence. That's the notion of a restart. And that works rather nicely, but again, you can see it's sort of expensive because we've generating sequences lots and lots of times over. We've multiplied up the number of times we're applying our linear operator, and that's increasing our computer budget. So the sort of state of the art, if you like, what a lot of these canned routines, library routines that you could use, will actually do is this notion of an implicit restart. And that's, basically following the restart philosophy, except as it goes along, it's doing this reconstruction, regenerating, rejigging the entire sequence as it goes along. So modifying the tridiagonal matrix as it goes along to see if it can construct a small set that has this nice property where the Lanchos sequence in this modified sequence appears to stop after L iterations. And that's done as sort of not, that in that sense you're doing these two things, you're combining these two steps in one. The restart is happening as the sequence generates. And we're monitoring this convergence criteria as the sequence is generated. Just to show that it works, I have a little experiment here just to try things out. Let's look at the Laplace operator on a triangle. So I've set the boundary, so we can imagine again this is a sort of triangular drum skin. And this is just a plot just to show that the technique gives us answers on a grid that's basically a sort of triangle that's 100 grid points along each edge. So the matrix is of order something like 5,000 by 5,000, roughly. And we pin down the edges, so we make this displacement 0 along the 3 edges of our triangle. And then we can use this technique to find the lowest eigenvectors. This is sort of the lowest resonant mode of this drum scheme, just sort of the bulk oscillation up and down. Okay, just to show it in action. So like I say, that would be an interesting question then to see if you could translate this into an MPI code to solve this problem about whether you can compute the spectrum of the Laplace operator in some complicated shape, and see if you could write an MPI code perhaps to handle that. An interesting problem to try and solve. There's a few so there's obviously some numerical issues with this, as I've discussed. You know, this notion of orthogonality is a tricky one to maintain. So restarting would probably be something you'd have to factor into your code. And then just the numerical precision you can get would be an interesting thing to address. Can you see with any precision differences in spectrum and similarities? If you were to compare two drum skins which ought to have a different spectrum, do you resolve that difference? How many eigenvalues can you track, and do you see clear differences, and do you see similarities between the cases which ought to match up? So do you get sort of a good enough precision out of your numerical experiments to say anything interesting about these drum skin problems? And can you parallelize it? Just how would you map these shapes into a data parallel MPI code? Okay, so whilst we're warming up, let's review again the other workhorse essential algorithm that every HPC expert ought to know something about, which is the notion of solving sparse linear systems. And again, let's keep things nice and simple and pick the easiest case where we have symmetric positive definite sparse linear systems. So again, our Laplace operator is our favorite example because it fits that definition. So you ought to know what the conjugate gradient algorithm is. I'm sure you've seen this before, sure. Good, so I can go very quickly through this. So again, here's an example, just to show you that these codes work. Let's, again, inside a triangle, let's take some Dirichlet boundary data on our displacements. So imagine now we, instead of a flat drum skin, we could perhaps have a sort of a three-dimensional shape. You can think of this as sort of a tent frame, if you like, and I'm stretching a canvas on a tent frame and trying to figure out what shape the canvas will take. And that is the solution to the Laplace equation with those boundary conditions being the displacement. So I've chosen the displacement to be 1 along the two the two perpendicular edges of my triangle, and then I've just to put a V shape on the hypotenuse of this right triangle, and then we can construct then the solution to the Laplace equation inside that domain. So that's the problem we're going to try and solve, and that is a sparse linear system again. So again, since we're just recapping, we'll go quickly through this just to remind you of the recipe. And there's a link again with this Lanchos method. They're both examples of these Krylov space-based methods. So they're constructing solutions inside a Krylov space. So we're generating a Krylov space on the fly through this iteration process. And it's going to be much smaller than the full vector space, but we're going to hopefully construct it in a clever way such that we can get close to the answer quickly. But essentially, we're going to try and construct approximate solutions inside this Krylov space. So the recipe for conjugate gradient is nice and simple to write down as well. We're trying to solve ax equals b in this example, and basically we take an initial guess of the solution is 0, in which case the residual, this vector r, is just b, and then we just generate again this sequence. So again, just put this up on the screen just to emphasize again the sort of functional property of this algorithm. The building blocks we have to assemble when we're writing a parallel code or code in general. What components do we need to glue together to write this, translate this into a recipe? And you see, again, the key point is that the matrix A, we never sort of dip into the matrix A at all. We never sort of reference individual elements and try taking linear combinations. We never shuffle rows and columns. We're never doing any of those sort of operations. A only appears on this slide again in essentially one place, essentially just multiplying the vector p. So the only way that our code, the only place we feed information in about the matrix A into our code is by writing a function that applies that, takes a vector, applies A to that vector, and spits back a new vector. So again, this is an enormous matrix. We're not explicitly referencing it. We're not explicitly writing it out somewhere in our computer's memory. We just apply it. So that's why these algorithms, such as conjugate gradient, are particularly suited to sparse matrices. And they will generally, depending on the structure of A, of course, parallelize quite nicely quite often as well. because most of our communication steps are going to be in the application of A to our data parallel vector P. And what else do we have in this recipe? Again, it's sufficiently short. You can see all of the steps. You have sort of Saxby operations where you take vectors, multiply them by scalars, and add them together. Those are very nice and simple things, of course. And parallelize very nicely, of course, provided we can distribute alpha quickly. And then there's dot products as well, of course. We need to basically evaluate the dot products of pairs of vectors. And again, that's simple to translate into code, but it can, of course, be quite an overhead when you're running a code on a large MPI machine, because this is a global summation being done there. So that could be, quite often that could be the most expensive step in this algorithm, actually the dot product step. Obviously, depending on what machine you're running on. So those are the three ingredients, which what makes this such an important sort of workhorse algorithm is its simplicity. Dot products, the matrix is just referenced through its application on a vector and these Saxby operations. And again, that's just very reminiscent. So this sequence has a lot of structural similarities to the Landshot sequence that we saw before. Okay, just dot products, Saxby operations, and matrix vector operations. And the mathematics behind it, the reason it works so nicely, is essentially you can show with a little bit of work, not too much, again using a sort of proof by induction to show this result, that this result, again, the resulting sequence of vectors that we generate, these R's and P's, these residuals and search directions, conjugate gradients, obey these orthogonality relations. So basically the R's are mutually orthogonal. There's an orthogonality relation between P's and R's, depending on the ordering. And there's a sort of conjugacy condition on the P's, which is this sort of funny insertion of A inside the P's. So it's not an orthogonality relation, direct orthogonality relation with the P's, but there's this conjugacy condition, and that's where the name of the algorithm comes from. So conjugate gradients comes from that last equation inside that box, essentially. These gradient directions P are conjugate according to this sort of modified orthogonality relation. And so the first line there, this orthogonality relation of the R's, tells us that basically, again, this sequence in exact arithmetic has to stop once we fill up the matrix. So after n iterations, where n is the size of the matrix, the sequence has to stop. It could stop earlier, of course. And then any subsequent values of this vector R is equal to 0, and R is a residual. It's basically the mismatch between the left-hand side and the right-hand side of my equations, and so we have to solve the problem. At that point, the value of the X vector that's sitting in our computer's memory is the one that solves our linear system. Now, in contrast to Landshot and eigenvalue solving methods, there's certainly round-off, which spoils all of these orthogonality relations again. But in general, we can worry a lot less about that for these conjugate gradient algorithms. It spoils conjugate gradients in a lot less dramatic a way. So Landshot is almost wrecked by round-off. You have to do a lot of work to fix it. And these restarting techniques are the way forward essentially at the moment, but there's all sorts of other things. You have to put in all sorts of extra patches to glue the algorithm back together after it's broken by round-off. But it's a lot less delicate here. Conjugate gradient is a lot less delicate. I mean, not to say it's perfect, certainly isn't it? It certainly goes wrong on plenty of occasions, but this the breakdown of these orthogonality relations leads to less severe problems than with Landshot. So basically what you do is you just keep going, essentially. What happens is this R vector generally gets smaller, and that's what you need. So you never get this exact stopping point, but that's after so many iterations you probably don't care. Generally R will fall off exponentially, and round-off wrecks these orthogonality relations, but it doesn't wreck the algorithm. Nice feature. When we go to conditions where the matrix A is not symmetric, positive, definite, things get a lot shakier there, and you can get more jittery algorithms in those situations. But here, when A is symmetric and positive, definite, round-off is a lot less damaging. And we generally speaking have a fairly stable algorithm. in under these circumstances. Obviously, as the matrix gets closer and closer to being singular, then the problem gets harder and harder to solve. So it takes longer and longer for the conjugate gradient recipe to converge, and so a lot of these round-off problems will have a longer time to ruin things, but in general, we have a reasonably robust algorithm.
Sorry.
Yep.
Can I ask a related question? So
Sure.
can one apply an algorithm such as GMRS to a singular matrix and get something meaningful for
GMRS. No, no. I mean, to get a meaningful answer there, you have to deal with the singular value in some way. So you didn't have to think about a singular value decomposition.
be doing something like Kuros or I don't remember the name. You construct a different problem in general to solve it.
But so that there you talk about a singular value decomposition. Yes, so you modify the problem essentially to redefine what you mean by the. You're essentially redefining the linear system actually to just be restricted to the subspace where you've thrown away the singular values.
Okay. Yeah.
So you have to go back to the original problem. And the original problem doesn't have a solution, so trying to ask the computer to solve an impossible problem is perhaps a little bit extreme. So you have to go back to the original problem and think a little bit more about what you mean by the solution to the original problem. And that means dealing somehow with the zero node in the linear system and just defining what you're going to do with that. So tweaking the original problem. So you're going to say, this is the original problem, but I'm going to modify it slightly to actually put a definition on what I mean by this singular part.
Something like a group Penrose definition of an operator is just.
I don't know what that is, but probably, yeah. The singular value is a trick where you basically you define a norm in the vector space of zero nodes of the operator, okay. And you say that I want that norm to take a particular value for my solution, and then that defines a solution now, but it's a modification of the original problem.
Yeah.
I suspect these other things.
Yeah, that's exactly
right. That's probably what these things are. Yeah, I don't know the right name. But you've got to go back to the original problem and fix it, because if it doesn't have the original problem, never mind. Before you can switch on your computer, the original problem doesn't have a solution if you have a singular matrix.
Or it has too many solutions.
Right, it doesn't have a unique solution, so I'm going to say yes, sorry. Yeah. And so you've got to tweak the original problem. Now, sometimes you can do that in a way that doesn't, if you think about a physics application, you can do that in a way that makes physical sense. You probably need to do that. But you're nevertheless going back to the original mathematical problem. So you're not relying on the algorithm necessarily to magically fix itself. You're going back to the original problem and tweaking it. And then you can write down an algorithm. Once you've got a well-defined problem, you can think about how you might solve it. But there is that extra step, which you should be aware of. So these singular value decompositions, they're in these canned routines, like LEAP, it has a singular, but it's not solving the problem you originally wrote down. It's solving a modified problem. So this is an important thing to recognize. And every time you say, oh, I'll just use SVD to solve this, you've got to think, oh, well, what am I actually, I've changed the problem that I actually solved. What am I actually solving now? So it's worth stopping and thinking every time you're sending data into an SVD code. There should be a little neuron in the back of your brain that triggers and says, okay, now I've actually changed the problem that I'm trying to solve. How have I changed it? And does that have dangerous consequences? Do I know what I'm doing at this point? Nevertheless, as retrieval then return you an answer, the question is what that answer actually means. It's worth stopping and thinking about. Yes, I mean, obviously, when the matrix is singular, the original problem doesn't have a unique solution necessarily. You've got to go back and think about what was the original problem that I was writing down. Does it make sense? Okay, good. So yeah, generally speaking, for the problems we're interested in, quite often we end up with stable solutions from conjugate gradient. So this little picture that I showed you here is solving the Laplace equation in this triangular domain with Dirichlet data, which means, of course, I've defined on the boundary of my triangular edge, I've defined phi to take a particular value. That's the Dirichlet data. But sometimes we want to study systems with different boundary conditions. And of course, the next example would be to think about von Neumann boundary data. Well, that is a constraint on the usually on the derivative, the partial derivative of the field, the first partial derivative of solving the Laplace equation, normal to the boundary. So, little picture here, I've drawn this a blue boundary, and the normal vector pointing into the boundary is that red line, and we would look along that, look for variations of phi along that axis and prescribe a value at the blue edge, that slope. So rather than saying phi has a value, I'm going to say the slope of phi as I run along that red line takes a particular value. And there's a von Neumann boundary conditions. So it's this dot product. And how do we put that into our mesh, into our finite difference scheme? And again, let's keep things simple, just for the sake of illustration, and stick with our square grid. And let's have a vertical boundary, the blue line in the right-hand picture. And so what we'd like to do is impose boundary conditions on phi on that boundary perpendicular to it. So that's running left to right. So we want to say that the slope of phi running horizontally at the blue edge should vanish. And of course, when I impose that constraint, I know nothing about the value of phi itself. I mean, it could be 1,000,000, and it could be 1, it could be -1. We don't know the value of phi anymore. We're just trying to say something about how it changes as we move into the bulk, from the white region across the blue line into the light blue region. And so, completely contrary to thinking now about our computer, the data inside our computer program, it's not like we can load a value into the array at that point and set things off again. What we have is now an equation. What we're going to end up with is now an equation, again, an active equation living at that site. So we want to have that. Now we're going to have an unknown living on the boundary that we have to compute. So just like with all the interior points inside the blue bulk, at every one of those red dots inside the bulk, remember we have an equation which we represent with this stencil, saying that the value at that point is the average of its 4 nearest neighbors, essentially, for the Laplace operator. That's what the equation is. Now we're going to need to write down an equation for phi on the boundary. But again, with these von Neumann boundary conditions, it's going to be a linear equation. And so we're just going to add in an extra bit to our unknown, an extra set of unknowns, which are going to be the values of phi on the boundaries. And they're going to have just different looking, sparse sets of equations to them as well. So they're going to be treated, the boundary condition points, the boundary data, are going to be treated exactly the same way, essentially. There'll be different coefficients. But we're going to treat them in just the same way. We're going to treat them as active, unknown entries in these x vectors that our solver is going to try and find for us, just in the same way as the bulk points are. So we sort of flip them around. So before, with Dirichlet boundary conditions, these values were sort of loaded into our array at the very start and held fixed. They were essentially part of the right-hand side of the unknown. I'm solving A, x equals b, they were part of b. And now for von Neumann boundary conditions, these unknowns, so the field values on the boundaries are part of the unknowns, part of the left-hand side, the x's. And so we've moved them. So we moved the boundary points out of the knowns and into the unknowns. To use the Rumsfeldianism. So okay, so just now, of course, what we need to do is just figure out very quickly what our linear system, what the coefficients look like at those boundary points. And the temptation is just to use a simple, the easiest possible representation of the derivative that we can write down. So, okay, so I want to, here's my boundary. 0, the value of phi here. I have my first grid point, phi 1 here. And I can obviously write down a representation of the derivative by just taking essentially the difference between these two things. And if I think of the Taylor extension about this point, you can see that represents the derivative with respect to the x coordinate at x equals 0. So you can see that's a simple thing to do. But of course, there's a term in that Taylor expansion that comes in at order h squared. What I'm doing, I'm just saying phi 0. A. So sure enough, I can represent the derivative with respect to x. I'm just taking the difference between these two things. But I get a correction which is only one power higher in this grid spacing. And if you think back to our stencil that we constructed to represent the actual bulk operator itself, because of its symmetry properties, it's that there are no odd powers of the grid spacing appearing at expansion, and we have an A squared output. So we sort of messed up our simulation by having to deal with these boundary conditions, these von Neumann boundary conditions. We're introducing a sort of an inaccuracy, an order A effect artifact, boundary artifact, which is going to slow us down in terms of convergence, getting accuracy out of our solutions. So we're going to have to run at smaller grid spacings to get accurate answers. And smaller grid spacings, of course, means bigger computer budgets. So can we do anything smart? The obvious trick would be to write down a symmetric difference of phi at this point. But to do that, we would need to know the value of phi outside the domain, and that's not going to be something we're going to try and compute. So we just don't have access to data over here. So we need to do a little trick, which is to just look further into the bulk. So we write down the value for phi over here. And again, we can rewrite this expression. There's two hops into the bulk. And A is still a small parameter, so I can still write down my Taylor expansion. Straightforward enough. And now you see I have a little bit of extra data. I've fed in a little bit of extra data, which is fine at this point. And now I can take linear combinations of these two expressions and kill off this term, which is proportional to A squared. And you see that's easy enough to do. Let's just take this expression multiply it by 4. Now if I take the difference, shuffle things around a bit, basically by taking linear combinations of these three numbers that sit inside my computer at these 3 points, I can write down a representation of the thing I'm after, which is this von Neumann condition, where all of the terms are being pushed up to order two powers in the grid spacing, so the same as my representation of the differential operator. And what I end up with now is a stencil that looks like the equation that I imagine living at this boundary point now. Remember, we have to make these active points and move them from the right-hand side to the left-hand side of my expression. So there's an equation living here now rather than a bit of data at the start of the simulation. That equation now just links not only the nearest neighbor but the second nearest neighbor. So I have a 2-hop stencil. That's going to complicate things in a little while, but we'll see how to resolve that. So then we just have to sort of treat these boundary points as a sort of special case. So instead of, in our code, we sort of have to have a conditional test that deals with the boundary values in a slightly different way. But again, you can see that we have another linear equation that I can pack into my sparse matrix. And after I run my conjugate gradient, well, okay, not the conjugate gradient in a minute. After I run my solver, then there'll be a value in this array that satisfies that constraint, along with all the other equations. And so you get an expression like this one here. So that's up there I have a representation which is accurate up to order h squared now, so I fix this artifact problem. And you see I need data from 2 hops into the bulk. And then if I wanted the boundary condition to be that the derivative with respect to x vanishes, let's say, it's nice and simple von Neumann boundary condition, the homogeneous one, then you get this constraint in this box here, which tells me the stencil I can read off from this point.
Sorry.
Yeah.
I don't really understand. So what was the artifact problem that we had?
Okay, so I need to represent the first order derivative with respect to x at the boundary, because that's the von Neumann boundary condition. So I'm posing a condition on the field here, which is the derivative, the first derivative with respect to x and phi, let's say it vanishes. So I need to write down, so I put my system onto a grid if I'm going to find a difference, and I restrict phi to data values in these points, and now I need to represent that differential operator as combinations in terms of these data, this data. So the simplest thing I can do is just consider the data point here and here, get the difference. And the difference is basically proportional to the derivative times the grid spacing, plus the second derivative times the grid spacing squared. So now there's only one power A difference between these two cases. So now let's imagine now my supervisor tells me that I want my solution accurate to 5 significant figures. So now I'm going to have to use a really tiny value of A, because the convergence, as I change A, the convergence to the correct solution, the artifacts that are coming from the fact that I discretize my system, are going to vanish only linearly with A. Whereas before, with the Dirichlet case, they were vanishing in A squared, so it was a nice rapid convergence. So if I wanted something that was twice as accurate, I only needed to shrink the grid spacing by 40%. Now I need to halve the grid spacing. So my computer budget shoots up. So that's bad news. That's just come because I've just tweaked my boundary conditions. There's all these millions of points inside the bulk that are being very accurately represented. And I've just messed things up on the boundaries here. So is there a way of avoiding that problem, making the convergence go still like A squared? And yes, there is. It's a simple trick. Basically, it's just to make sure that when we represent the derivative here, we write a slightly fancier representation of the derivative, which looks not just one hop into the bulk, but 2 hops. And we have to hop to the right because we don't have any data outside the boundary. It's not defined. This is empty space. We've fallen off the edge of the world here, so there's no data over here for us to use. So we have to keep moving to the right-hand side. But if we move 2 hops, then we get sufficient information from these 3 values here by taking linear combinations of those 3 values to write down a representation of this derivative, which has these are the corrections of the order. By taking 4 times this expression here, which is the Taylor expansion at this point, and comparing it to the Taylor expansion at this point, if I just take the difference between these 2 things, now you see the coefficient in this term here is the same as this term here. So when I subtract these 2 things, I get 4 5A minus 5 2A is equal to 3 5 0. Plus 2 A plus nothing, those terms are going to cancel, plus order. And now I move this across to the side. By 2A. Now I have a representation of the derivative of the boundary, which is what I want, plus, because I divide by A, this is come down to order A squared, not order. So now my supervisor wants his 5 significant digits of precision. Hopefully, I still have that property that if I decrease my grid spacing by 40%, I double my precision. By precision there, I mean the size of the artifacts that I've introduced by putting in a finite grid spacing. So it's just a simple trick to make sure that when I put in Van Neumann boundary conditions, I don't mess up that convergence. I don't slow the convergence down in this quite artificial way, just because of the boundaries. It's a set of measure 0 compared to all of these bulk points, millions of bulk points which are behaving themselves very nicely. We've just introduced these few badly behaved. Okay, does that make some sense now? Yeah. And obviously, this is sort of specific to this first order derivative. The recipe follows. If I need higher order derivatives and I want to constrain that, maybe have a more complicated differential equation. This recipe, you can still apply recipes like this one. If I needed to represent third order derivative, I might need 5 data points or something like that. But you can follow the same recipe. Just keep going and construct these more complicated terms. So it's a more general principle, at least, when you consider different differential operators. Okay, so running a little bit out of time now. Let's just think a little bit now, just to finish up this morning, how we might write the parallel code, and what's going to be the sort of design issues we need to think about. And so the nice thing, like I say, about these recipes is that the building blocks are very simple ones. We never explicitly write down this matrix. Implicit in all of these equations is a very large linear system. I could write out this matrix, it would be enormous, but I'm never going to do that. I'm never going to explicitly load that matrix into the computer. I just need these Saxby operations, which are just linear combinations of vectors. They're pretty simple things. I need to evaluate dot products, and then I need to add a function. So the place where the matrix actually appears is where it's encoded into our software. It's a function which applies the linear. It takes a vector, writes a new vector, which is the result of applying the operator to the input. And so that can be done in code in a sort of mechanical way, taking account of the sparseness, and to just take linear combinations and small bits of data in a very efficient way. That's why sparseness is important in that step. So let's think a little bit about how we translate this into MPI code. So this is actually pretty straightforward usually. We're making assumptions that these two vectors that we're adding together are data parallelized in the same way, of course. If they aren't, then of course we do have a problem. We'll have to think about communication. Let's assume that that's laid out in the same format, if you like. And dot products can be easily written as an MPI code. I mean, there really is literally, in its simplest implementation, and I wrote one for you there, it really is, 2 lines. So here's how you write a dot product of a data parallel vector into MPI. It's really a single MPI call. Now, I mean, obviously, you might want to write a slightly fancier version if you actually wanted a robust piece of code, but never mind. Just to show you how simple it is when you break it into an MPI call. So MPI has this function, MPI or reduce, which generates a value on all possible MPI processes, which is got by taking some set of data on all of those processes and reducing them. In this case, it's going to add them all together. That's the MPI sum step. And what are the numbers? Well, they're the part of the dot product that's been computed locally on the little stretch of the vector that's stored locally on each MPI call. We evaluate that part of the dot product. And then it's a single double precision number in this example. And then we reduce it as an MPI sum. And then the answer is this thing that comes back out of the MPI function. So writing dot products is very straightforward as a starting point. But of course, when we run on big computers, we might have to worry about the fact that that MPI or reduce set is sending data from every MPI process to every other one. Now, how that's being done, you have to rely on the engineers who've written the MPI library for you. Hopefully, it's been done in an efficient way. And there are certainly some fancy tricks for getting that to be done quickly. But nevertheless, data has to move from everywhere to everywhere, essentially. So quite often, if you sort of just naively count floating point operations in codes like this, it looks like that applying the operator, this third step, might be where all the floating point action is happening. But quite often nowadays in modern codes, these global sums, these reductions here, depending on the machine architecture, can be really the thing that takes all the time. And then if we want to think about our linear operator, again, if we're representing differential equations, so if we're taking sort of physics application, then we normally have these sort of nice, simple patterns where we really think of a grid of data, and we're just taking nearest neighbors. So most of the data is sort of fairly local, and the only thing we have to take account of is when there's a boundary in between MPI processes storing bits of data, and obviously then when I'm computing the action of on a class operator at this point, I need to know information that this other process is storing, so send it. And the code we've written in an infinite infinitely many different ways. One of the sort of easiest ways to implement this in code is basically to add in as an extra boundary layer, which essentially looks like Dirichlet data. So the process 1 doesn't change this value, it's going to store this value, but not change it. So it looks a little bit like Dirichlet data. So again, we get pictures like this, where we take our domain, we're trying to solve the Laplace equation inside a square, break it into chunks, and again, because of the structure of the problem, where our representation of the Laplace operator has this locality feature, then it's very natural to try and keep the data together. Because now we're minimizing the communication required to evaluate, to do this last step, to apply the operator to the data. And so the usual way we might choose to code this would be to sort of add a halo, where we basically add a set of points outside the red square, one hop either way. We allocate memory inside process 0 to store that information, and we load that information in by MPI exchange. Communication steps where we load in from the other processes, the neighboring processes, load in values just off that red box. And then the task for optimization, if we're thinking about writing a modern code that's efficient, the tricks that people play with this part of the code is to see whether sort of computation step, actually evaluating the value of the vector at each one of these internal points, can be overlapped with communication steps. Yeah.
Well, halos, so again, so each processor has local halos basically at its boundary, and these are stored on the respective processor.
Let's take this picture here. So let's imagine we're trying to solve this problem here. We're trying to work out these 16 numbers that are going to live on the white grid points here, and I've got Dirichlet data on those green points. So my problem's defined, hopefully. And let's run it on 4 MPI cores, and each MPI core is going to try and work out 4 values. So that's that picture. That's what that picture up there is telling me, right? So what would I store on process 0? So let's chop out part of the problem sitting on process 0. So let's just cut out what's inside that red square. So I need obviously to store 4 numbers. And of course, when I'm evaluating the operator at this point here, I need to know values here and here. Well, those are just the Dirichlet data. So let me pad my array here with values, which are just going to be, so now my array is grown slightly. And just at the start of the simulation, start of the calculation, I'm going to load in the Dirichlet data into these points here. Okay? But I'm also going to pad the array, let's draw a different symbol, on these other 2 sides as well. And these are going to be my, so this is Dirichlet data. Which I set up at the start. But functionally, in terms of from sort of software point of view, I'm also going to pad to the right-hand side below. But now I don't know the values here at the start of the simulation necessarily, and they're going to change because these are unknowns. They're representing the data that's just off that red square to the right-hand side. So these things, let me give these a name. Let's call these the halos. So my array, what started out looking like I was going to have a little 2x2 grid of 4 double precision numbers on this process. I'm actually going to store effectively a 4x4 patch of the problem. This region here is just going to store the Dirichlet data. And this region here is going to be a buffer that will be loaded by MPI calls. Right? So as the calculation runs, every time I need to know the value of the field 1 hop to the right of this point here, which I did in order to evaluate the Laplace operator here, I need to know this value. I'm going to look inside this array and hope that at the appropriate time, that's been updated by an MPI call by sending data from processor 1 or whatever it is into this halo. So processor 0 is going to be responsible for evaluating numbers on these points. And in order to do so, there are going to be MPI calls that will send load numbers into these parts of the array. So the array has quite a complicated sort of internal bookkeeping now. The patches of the array that just never change. The patches of the array that the process is responsible for updating and computing. There are patches of the array that the MPI process, receives information into, from MPI sends and receives. And then don't forget, of course, on process 0, we're going to have a similar looking picture now. Except this will have a halo region to the left. Sorry, process 1 now. And process 0 is going to be responsible for sending at the appropriate time. Obviously, you've got to coordinate and synchronize these steps. Sending these new values that it's just computed through an MPI instruction into these halo points. But in terms of the code, you know, so when we're actually applying the Laplace operator, process 0 will loop over sort of, this is a local index, will loop over sites 1 and 2 only. It'll only loop over, it'll only compute in this region here. These values will stay fixed, and these will be updated through these MPI send and receive steps. That makes some sense?
Yes.
Yeah. We'll look at some code after lunch, maybe. That'll make it a little bit clearer. Okay, I think we can finish up there. Yeah. Let's finish up, and we'll maybe look at some example bits of code after lunch, and we can see sort of how you might turn that into this scene. So, and see how that works. Okay, good. So I'll see you at 2 o'clock, right? Back here.
In this one or the other one? So you mentioned that there will be like lab sessions somewhere.
Yeah, that's later on. Yeah, the lab sessions will be upstairs, but we have another hour of yours truly at 2. Okay. So back here at 2 o'clock. It's probably not a great idea to leave things in here. If you want to pack it up, I can put it in my office. This is only just upstairs, and I can bring it back down for you at 2 o'clock. Should we make sense?
Yeah,
Do you want to do it? Yeah.
just the camera.
Oh, with things set up. Yeah. Could leave them. Yeah. I could ask them. I could get locked up again too.